Hi everyone, and welcome back to our YouTube channel. As you all remember, in the previous lecture we learned how to convert an electric circuit into a problem to find the solution to a given system of linear equations. And in that example actually I used Ohm's law and Kirchhoff's current law. In other words, I applied the nodal analysis technique to analyze the circuit given to us. And in that example we found the voltage values. Now in this lecture I changed the roles. This time I will apply mesh analysis technique, and I will show you how we can apply this technique as well. Okay, in this way, this time I need to use the Kirchhoff's second rule, which is actually stating that we conserve the energy around a closed loop. That is, if you find the algebraic sum of the voltage rises and drops in a given loop, then it must be equal to 0. Alright, I will use this rule along with the Ohm's law to find the currents given in this electric circuit shown in this example. Suppose we are given a circuit like this. So here in this circuit actually we have elements. Let's first define what these elements are. So the elements shown in the Ohm's values that are just circled in black, these are the resistors, right? So we have 10 ohm, 20 ohms, and 5 ohms resistors. So we have three resistors, each of whose resistance is given as shown. And we also have two batteries. One is 40 volts and the other one is 20 volts. And also look at the poles given to us. So the direction of poles also is important for us when we try to construct the equations. And if you notice, we are also given two direction of flow of currents. And in this mesh, in these two meshes, actually we have two meshes here, right? We have two meshes. And the first one is this mesh, as you see. And we have the counterclockwise direction here. As you see, this I2, which is the second current value, actually is used to represent that in that mesh, in that specific mesh to the right hand side, the current flows through clockwise direction. And in the left again we assume a direction for the flow of current, and in this mesh also it is selected as through clockwise. So these are important because I will form my equations with respect to these meshes. Alright, then how will I do that? Well, it is pretty similar to the one that we applied Kirchhoff's current laws, but this time I will apply Kirchhoff's voltage rule. So in other words, in each mesh, both actually on the right hand side and on the left hand side, I will apply KVL, Kirchhoff's voltage rule, to find the equations. Okay, let's start with the first one. And now the algebraic sum of these voltages should be equal to 0. Okay, let's start by taking into account the direction of the current as well. So we know on the left hand side we have the current flow through clockwise, right? So this is important on the left hand side. So we know this. So the current flows in this direction, right? So this is important here. And also the current enters the battery, the voltage source at the negative pole here. And this is also important. I need to take into account that point. Okay, and by the way, I assume the clockwise direction negative and I assume the counterclockwise positive. That's just an assumption. That doesn't need to be true, but we need to prefer one of these directions. So again, I selected the clockwise direction negative, and counterclockwise direction positive. All right, let's now find the algebraic sum in the first mesh, on the left hand side. So start with the 10 ohm resistor. So we know that now we need to use Ohm's rule. Okay, what does Ohm rule say? And Ohm's rule or Ohm's law says that V is equal to I times R, right? So the voltage across a resistor is equal to the multiplication of the current by its resistance. So in this manner, what is the voltage here? So the current is I1, right? In the first mesh on the left hand side, the current flows through this part of the circuit is equal to I1. So for the 10 ohms resistor we have, and of course by assuming the direction of the flow negative because it is flowing through clockwise, and we suppose that the flow through clockwise is negative, then we have minus 10 I1, right? So this is the voltage drop or rise that is passing through the resistor, which is 10 ohms. And continue for each element on the left hand side. How about the 5 ohm? The thing is, we should be careful. We should be really careful here, because the 5 ohm resistor is placed at the intersection of two meshes, so it is affected by both sides. So on the left hand side, what is the value? It is 5 times minus I1, because on the left hand side the current flows through clockwise and it is assumed negative. This negative sign comes from that fact, and 5 comes from the value of resistance, and I1 is the value of current. But there is one more important thing. You know, it is also evident that there is this current flow in the negative direction. So what is the effect? So we have negative direction here, right? So what should I do? Then I use the positive sign. So this is 5 times I2, because the contribution of the second mesh on the right hand side on this resistor is in the reverse direction, right? So 5I1 comes from above to below, and 5I2 comes in the reverse direction. And also 40 volts of battery, so the current flows in the battery at the negative pole, which means minus, we take minus 40, right? So you see, that's the voltage value. So minus 40 minus 40 is equal to 40. And this should be equal to what? This should be equal to 0, right? Because the algebraic sum of the voltage rises or drops must be equal to 0. And let's right. Okay. Now we have the first equation, and what the first equation says is minus 5I1 plus 5I2 is, and also there is also 10 minus 10 here, so make it 15, right? Minus 15I1 is equal to minus 40, right? If I move 40 here to the right hand side of the equality, I got minus 40. And this is the first equation for the first mesh. So for the first mesh, now I have an equation where the only unknown values are the current values in each mesh, right? This is what I am trying to find. So if I want to find the values of the currents in each mesh, then I need to write my equations in terms of these unknown variables. And for the second mesh, I do the same thing. So I will have another equation. Let's do it. So let's start. So 20 ohms. Okay, let's start again with the resistor. So what do I have? So I have minus 20, and the value of current in the second mesh is I2, and you know the direction is here through clockwise. I take negative, so minus 20 I2, which is the voltage across that resistor, right? I apply the Ohm's rule. I multiply the current by the resistance, so we have 20 ohm resistance, and we have I2 as the current value, right? And we have the direction minus, so because the flow, actually the current flows through the clockwise, which we assumed to be negative. I continue in this manner, so I look at this direction, and it enters the battery at the positive pole, so I just take the sign negative, no change in the sign, just minus 20 volts here. And again, I come to the intersection point, but this time 5I2, again 5I2 is in the negative direction because it is the value of this mesh. We have I2 as the current value, but in the reverse direction we have also what? We have also 5I1, right? This is the contribution from the left hand side mesh. So don't forget to add this value. So it is just like taking the difference, right? We don't know which one is bigger, right? But what we know is if one comes from one direction and one comes from other direction, then we need to take the difference, right? This is nothing but this. We just take the difference. So I assume one direction negative, whereas I assume one direction positive, right? If I assume the clockwise negative, then the counterclockwise is equal to positive. So it's just like taking the difference between I1 and I2, which is placed at the intersection point of these two meshes. And in the first equation I did the same thing, but this time I subtract I2 from I1, right? Because the flow of I1 is in the negative direction. So I have another equation, okay? If I rewrite this equation, then what I have here, so we have 5I1 and minus 25I2 is equal to 20. So this is the second equation. Well guys, as we all see, we are at a very good point. So what I have found so far? Well, I was required to find the currents depending on the electric circuit given to me in the first place. And to do so, I applied Kirchhoff's voltage rule in each mesh. So we have two meshes. That means I will have two different equations. And since I am required to find the current values, my unknown variables should be the current values in each equation. And I used Ohm's rule to define the voltage in terms of the current values, which are the unknown variables as I said. And now I have two equations, which means I have a system now. I have a system of linear equations. And how I succeeded it? I simply used both Ohm's law and Kirchhoff's second rule, Kirchhoff's voltage law, right? So the conservation of energy rule is used in this example. And what is left behind is I just need to solve this system. I can use the elimination method, I can use the Gaussian elimination method, or Gauss-Jordan, or any other technique that I know. But from now on, it is very simple. So, for instance, if I write these equations, minus 15i1 plus 5i2 is equal to minus 20 and 5i1 minus 25i2 is equal to 20. So what should I do? If I multiply the second equation by 3, right? If I multiply the second equation by 3 and then I perform an element-wise addition, then the I1 values are cancelled. Then what I have? So 3 times minus 25 is equal to minus 75 plus 5 is minus 70 I2 is equal to 60 minus 40, 20, and dividing both sides by 70, which is the coefficient of the unknown variable I2, right? Minus 70 actually. Now we have what? We have I2 is equal to, well, cancel out these zeros, minus 2 over 7. This is the value of I2. And if I plug this value of I2 in one of these equations, then I find the other unknown variable, right? So I found the second current value, in other words, the second mesh value, and put it in one of the equations. Say I put this value in the first equation, then what I have? So 15 minus 15i1, 5 times minus 2 over 7 is minus 10 over 7 is equal to minus 40. And let's isolate I1 and move this value to the right hand side and then divide both sides by minus 15. So what we have here, so minus 15i1 is equal to minus 40 plus 10 over 7. So denominators are different, so let's equalize them. Multiply by 7 to do so. We have minus 280, and so minus 15 I1 is equal to minus 270 over 7 and dividing by minus 15, we have the desired value of the unknown variable of I1, which is the first current value in the first mesh. So we have I1 is equal to, and also, you know, minus minus, we divide, when we divide minus by minus, it's positive. So 270 over 105. We can also cancel them out by 5, right? So it's possible. Right, this is the value of I1. So what it means? Well, we started with a given electric circuit and we are asked to find the currents, and we applied both Ohm's law and Kirchhoff's voltage law to construct a system of linear equations in terms of the unknown variables, which are the current values in this case, and then solve the system by one of the techniques that we are familiar with. Since we have a 2 by 2 system here, we have just 2 equations and 2 unknown variables. I simply used the elimination method and I found the values of the unknown variables. Right, and this is how it goes. And as you notice, in the last 2 lectures, we solved a problem, a fundamental problem that you can come across in the field of electrical engineering, by using systems of linear equations. And in this lecture, I applied mesh analysis technique. And hopefully you enjoyed this video as well. Alright guys, that's it for this course, for this lecture. And see you in the next lecture.